Hey guys, so last time we talked about the multiplication rule and how to apply that a little bit. Now we're going to go into advanced applications. And so what I mean by that is not just the independent rule, not just addition rule, and not just complements, right? So we're going to focus on everything all put together, and we're going to do some kind of more advanced problems and see how we can go ahead and learn from those. So let's go ahead and start off with our advanced applications. So the the multiplication rule can be applied for more than two events as well, right? So if we're talking about independent events or dependent events, we can actually take into account more than just two events, as we've seen before, right? So let's go ahead and look at example number 1. What's the probability of rolling a die 5 times and getting a 6 every single time? So that's basically the probability of getting a 6 times the probability of getting the 6 again. Why don't I include the given in there? Because I should say the probability of 6 times the probability of 6 giving me having rolled a 6 the first time, right? The reason there's no given is because these two events are independent. Right, so again, rolling a die, even though I got a 6 the first time, that doesn't affect the probability of me getting a 6 the second time. Right? So just keep going. Times the probability of getting a 6. And how many times are we rolling this die? 5 times, right? So the probability of getting a 6, 1, 2, 3, 4, 5 times. Essentially, this is basically like saying the probability of rolling a 6 to the 5th power, right? Because we're multiplying 5 chances of getting a 6 over and over again, right? So what's the probability of getting a 6? So the probability of us getting a 6, there's only one 6 on each of the 6 faces of a die. So it's 1 out of the 6 faces, right? So once we go ahead and do that, we get 0.00013. Cool? So there's basically like 100% of a chance of you rolling a 6 5 times. Does that make sense? Cool. So for the intersection of events, other possibilities also need to be considered. So here we're talking about, again, a string of events, right, happening one after another. There could be some multiple possibilities for the string of events to happen. So if there are multiple versions of any given intersection, we use the addition rule to take into account these other possibilities. So the probability of A and B happening may sometimes turn out to be the probability of A and B happening this one way, plus the probability of A and B happening another way, and another way, and another way, and another way. So you have to take into account all the possible different ways that this can happen. So for example, what's the probability of flipping a coin 4 times and getting heads twice, right? So if we just, in general, didn't even think about the order of these things or anything, the probability of getting 2 heads, we would probably go ahead and assume that it's probability of a head, a tail, and a tail. Let me put these caps. So head, tail, tail. And so it's basically the probability of head times the probability of head. Now why don't I include a given in this one? Again, for the same reason we didn't in the other one, right? Because flipping a head does not affect the probability of me flipping a head again. It's totally independent events. So times the probability of tails times the probability of tails. So we would get 0.5, right? That's the probability of getting a head the first time. Second time, doesn't change, right? We're talking about independent events. So it's still 0.5, still 0.5, and still 0.5. aka 0.5 to the 4th power. And that gives us 0.0625. But now, that's only one way that this combination of events could happen, right? I flip a heads first, twice, then tails, tails, right? Because that's 2 heads, 2 tails. Now, what are some other possibilities? So that's one way, is heads, heads, tail, tail. What are some other options? We maybe got a heads first, tail next, head first, tail next. Head first, tail, tail. So head, tail, tail, head. Another one is tail, head, head, tail, tail, head, and tail, tail, head, head. Right? So there's a total of 6 different ways that this can happen. So what we basically do is the probability of each of those, which actually, are they any different than the probability that we found here? They're actually exactly the same, because at the end of the day we're multiplying 0.5 4 times, right? Because for example, the first one was head, head, tail, tail, 0.0625. But the next one, head, tail, it's still 50% head, 50% tail, 50% head, 50% tail. So we still get 0.0625 for each of these 6 different ways. Now, what did we say earlier? Once there's different ways for this to happen, you do the probability for each particular outcome, or each particular version of this string of events, and add them up together, right? So it's basically 0.0, so probability of 2 heads, period, is 6 times 0.0625. Why is it 6 times that? Because essentially this would have broken down into 0.0625 plus 0.0625 plus 0.0625, and it would have kept going 6 times, right? So it's basically just 6 times the probability of one of the ways happening. And so the probability of us getting 2 heads, taking into account all the different ways that this could happen, ends up being 0.375. Or 3750 if we want to stick to our 4 decimal place rule. Cool? So let's move on to example 2. A bag contains 5 green marbles, 3 white marbles, and 4 blue marbles. Find the probability that, when drawing 2 marbles without replacement, what does that word tell you automatically? Without replacement. I guess 2 words, right? So, without replacement tells us that it's totally independent events. Right? I'm sorry, dependent events. Because if we're not replacing them, we're basically changing the number of marbles every time. Right? And so the probabilities associated with those marbles, or picking a particular marble, changes. Very cute drawing, right? I tried hard to make that one. So 2 marbles are the same color. So what are some possibilities? We have green, green, right? Blue, blue, and white, white. So what are we going to do with these 3 different versions of string of events? We're going to go ahead and add them up, right? So again, just the addition rule. So what's the probability of getting 2 greens? Right, so we're going to say the probability of getting 2 greens, the probability of getting blue, blue, and the probability of getting 2 whites. So the probability of getting green, green is, first time is 5 out of how many total marbles? So we have 5 green, 3 white makes it 8, and then another 4 blue makes it 12. So 5 over 12 times, actually do it this way. Now it's the probability of me pulling another green if I did this without replacement. How many greens are left? 4, right? How many marbles are left total? 11, good. Cool, so that's the probability of green, green. Now we go ahead and add that to probability of blue, blue. So how many blue are there total? We have 4 blue. And how many total marbles again? We're not going to say 10 because we're treating these as totally different events, right? So either blue, blue, green, green, what's the probability of that happening? Now, hypothetically, let's say we pull a blue first this time, right? So we're not actually just following along with green, because that would be me pulling green, green, blue, blue, white, white. That's not what we're asking. We're pulling 2 marbles, what's the probability it's the same color? So we say green, green, here's that probability. Now let me go ahead and just forget about me pulling 2 greens and start off with me pulling a blue first. So it's 4 over 12 again. And then how many blues are left once I pull out 1? 3. How many marbles are left? 11. Plus the probability of white, white. So how many whites are there initially? We have 3 whites out of 12. Pull 1, we're left with 2 and 11 marbles total. Right? So we get 20 over 121 plus, and this I'm just multiplying out green, green. Now blue, blue, it's 12 over 121. And the last one is 6 over 121. Once we multiply all that out, we end up getting 0.3003. Cool? Next, so in problems that ask you to find the probability of at least one event occurring in a string of events, it may become difficult to find that particular probability, because if you're saying, for example, the probability of flipping at least one head, right? That's a simple example. We basically have to say, what's the probability of flipping one head? Because we want at least one, so we want to know one head and more, right? Up to however many times we want to flip this coin. So if we say the probability of at least one, it's the probability of one or more. So we have to do probability of flipping and getting heads once, probability of flipping and getting heads twice, 3 times, or thrice, let's get fancy, 4 times, 5 times. So we have to do these multiple calculations that get very annoying and very tedious, and there's a lot of room for error. So then what we can do is use complements to help us out. So remember what complements were from back in the day? It's basically all outcomes not covered by a particular event. So, in particular, what would be the complement of getting at least one head? What do you guys think? It's a little kind of conceptual type of question, but once we get it down packed, we're good to go. The complement of getting at least one head, if we're flipping a coin, for example, 25 times, it's the probability of getting no heads, right? Because what we're left with is, let's say this is our whole series of outcomes, right? If we have our whole string of outcomes and we say the probability of 0 heads, probability of 1, let's say we flip this coin 5 times. Or 4, because I'm tired of writing numbers. So we flip this coin 4 times, there's 5 outcomes, right? We can get no heads, 1 head, 2 head, 3 head, or 4 heads. Cool? So now, if we say at least one head includes all of this. Right? This is at least one. But now the complement of that is all outcomes outside of at least one. So outside of at least one, the complement would be 0 heads, right? Or none. No heads at all. So let me go ahead and put this a different color. Probability of at least one, the complement is the probability of none. So for example, another thing I want to point out is, what's the probability of all the outcomes put together? Or the probability of a sample space, right? The probability of a sample space, or if we take into account all the possible outcomes, it should equal 1, right? Because there's all the probabilities associated with each of those outcomes, but all together we have 100% because we're covering all the possible, basically, outcomes that we can run into. So if this whole thing is 100%, right, we can say that 100% minus at least 1, which is this chunk here, right? 100% minus the probability of at least 1 is the probability of none. Or, same thing around backwards. Moral of the story, probability of at least one head is 1 minus the probability of none. Right? Because 1 is everything minus the probability of none, so I take out none, and I'm left with at least 1. So that's the way we can do those and apply a complement to make our lives a lot easier. So let's go ahead and do a practice, an example, and then we'll move on to practice right after this. So Florida is one of the highest accident rates in the country. Assuming that you have a 30% chance of crashing when you drive, totally made up, I don't know what it is. What is the probability that out of the next 20 times you drive, you get into at least one accident? So again, let's go ahead and figure out what are we looking at. So probability of at least one accident, what we'd have to do is the probability of getting one accident plus the probability of 2 accidents plus, and we'd have to go all the way up to what? At least one, you're going to have 1, and all the way at a maximum of how many? You're driving 20 times, so the most accidents you can get into in 20 times is 20 accidents, right? We can go ahead and find probabilities associated with each of those, add it all up. It's going to take us forever though, right? So let's go ahead and apply this complement rule. So the probability of at least 1 is also just 1 minus the probability of getting to no accidents, right? Cool. So what's the probability of getting into no accidents? 1 minus the probability of not getting into an accident how many times? It's not getting into an accident 20 times, right? So to the 20th power. Does that make sense? So I'm kind of bringing back a little bit, kind of when we went up here. A string of events, we could just say it's the probability multiplied by itself 5 times, right? Or if we're talking about rolling a 6 5 times. So let's go back down here. Here's not getting into an accident 20 times. And so we're going to consider them completely independent because you not getting into an accident the first time, it's not like you go your next time driving you feel more confident, right? It's just like another day. You just go and drive, you don't even notice that you didn't get into an accident. Does that make sense? So these probabilities or the events are completely independent. You not getting into an accident one day does not affect you not getting into an accident the next day. So here's the probability of getting into an accident multiplied by itself 20 times, and that's the probability of getting into no accident out of those 20 times, right? But that's only one out of our entire sample space. We don't want the probability of none. We want the probability of at least one. So we say my entire sample space probability minus this one outcome gives me all the other outcomes. So equals 1 minus, what's the probability of no accident at all? If there's a 30% chance of you getting to an accident, what's the probability of not getting to an accident? 70%, right? So we're going to say 0.70 to the 20th power, right? And sadly, this ends up being 0.9992. So if the rate was actually 30%, for every 20 times you drive, you should expect to get into at least one accident 99% of the time. Almost basically one, right, if you round it off. But good to know that's not actually true, right? And so that's our probability applications of these advanced rules. And so these might not actually be separated in the book, but I like to separate this as a whole different topic because this is not only just one of the rules, it's multiple rules and complements being put together. And so it really demonstrates that you're able to understand these probability rules and how to apply them efficiently. So let's go ahead and move on to practice problems, and that's about it. So see you next time.